I love experimentation. Most of all, I like doing experiments with my own hands. So as soon as I think I know what's going on, I want to check it with an experiment. I want to make it myself. Nothing's more exciting than doing experiments myself. In the field of organic synthetic chemistry, compounding has to be precise. Make a mistake, and you sometimes get polymerization. The word polymer covers a litany of sins, so I wasn't keen on this line of research at first. Once I got started, though, I realized that a polymer was a material in a chaotic state of molecular weight distribution. I was hooked. What's fascinating to me is that the same polymer can demonstrate completely different properties. Biodegradable plastics have been known for decades, but they never gained currency because, as the name says, they're biodegradable. They immediately break down and degrade. They're poor in reliability, and that problem had to be solved. For example, microorganisms exist in the environment, so to break down a biodegradable plastic, all you have to do is place it on top of a clear slide. In that state, it's not a very useful material, so we needed to insert a switch that could prevent dissolution. The switch could be something triggered by light, heat, moisture, pressure, pH, or something else. However, one feature of the ocean surface environment is that it is subject to strong direct sunlight with no shade. So we chose to develop a switch that is triggered by light. We developed two types of switches, an on switch and an off switch. The basic idea behind the light switch polymer is that we insert it into a polymer that is not biodegradable. When light irradiates it, part of the polymer is hydrolyzed, generating carboxylic acid and an amino group. These components make the polymer hydrophilic, promoting formation of a biofilm. The entire polymer then biodegrades. Half a dozen organizations collaborated. AIST handled the main work on material development. The light catalyst for the on switch was developed by Tokyo University of Science and Tokyo University of Agriculture and Technology. Evaluation of the action of the light switch and biodegradation was performed by AIST, ORIST, Kagoshima University, and Kobe University. Kobe University also carried out the safety evaluations. The key moment in making the material itself was the design of the switch that exhibited the biodegrading behavior we needed. I was overjoyed when we accomplished that. And when we announced the breakthrough at exhibitions and so on, the excitement we received was the greatest blessing a researcher could hope for. One issue is improving the performance of the switch. Poor performance would affect the material's properties. If the switch fails in the on state, breakdown won't be triggered, and the material will be nothing more than floating trash. So switch performance is the most important factor of all. The type of switch needed depends on the conditions under which you want the material to break down. So different switches are prepared for each application. It's important to think in terms of using different materials for different purposes. Population growth itself has a significant impact on the Earth's environment. What can science and technology do about it? One thing we can do is instill the spirit of MOTTAINAI. One specific implication of MOTTAINAI is thorough implementation of cascade use of energy and materials. It is vital that we optimize our lives for recycling of materials in harmony with the Earth's natural environment. Plastics make life easy and convenient in many ways, but they have become a social issue. We are using the power of light to build a prosperous society and contribute solutions to the problem of marine plastics.
NEDO